like point X on Mohr circle. This is point Y on Mohr circle. So based on this orientation, okay, we know that stress X is equal to 0, stress Y is equal to positive P over A, right? And the shear XY is equal to shear YX, and is also equal to 0 because the way it's loaded. Okay, it's only unidirectional if our element is right in that orientation, 0 orientation. So in fact, this is the element is at the principal plane. Orientation. This is because, okay, this is because the shear is equal to what? 0. Okay, so we know about that. Okay, there's nothing we can. Then we are going to orientate the element at 25 degrees. Okay, so 25 degrees, bear with me. So our element now is at 25 degrees. Yeah, so about here is 25 degrees. Okay, so this is 25. Then I'm going to rotate it. So now the element is rotated, okay, from the horizontal, right, and then it's going over here in the clockwise direction by 25 degrees, right? So because it's going to rotate from Y, as in Y here, this is my Y25, and this is my X25. Okay, that's how I'm going to leave it. So we have no information about all this, right? So we're going to find the points, okay, of the we're going to find where is Y and X and Y25. You don't need to find what's going on X25 because this is the region of the glue. Okay, so this one I'm highlighting now. This is where the glue is, right? This is where it's important. So X25 is not critical. Okay. So now I'm going to construct Mohr circle. Okay, I'm going to construct Mohr circle. Sketch again. So this has more tensile. Okay, so I'm going to draw tensile. Yeah. I'm not a pink guy. Then this is our shear. Okay. So this is our normal stress, shearing stress, element rotating clockwise, element rotating anti-clockwise. Okay. So we know that point X is over here. And this is our point Y. Okay, our point Y. So we draw our circle. So this is our circle, right? And we know this distance, by the way, okay? So we know the distance from here to here. I'm going to go into distance. So we know the distance from here to here. Right? This distance is P over A. Right? And regardless of, I think the most important thing of this problem is this. The stress average for both the element oriented at 0 degrees and at 25 degrees, okay, are the same. Okay, so I'm going to write down here that the stress average for both 0 degrees and 25 degrees are the same. Okay, so therefore, okay, they are the same. Okay, so therefore, the center point of the circle is at the fixed position. Okay, that's what I wanted to know. Okay, so we know that this is our stress average, right? So over here, this is our point naught, right? And then I'm going to draw. So the distance from here to here, right? Distance from there to there, right? So this is P over 2A. Okay. So what we know is the element will rotate by 25 degrees in a clockwise manner, right? So on the element from point Y, it will rotate 50 degrees. Okay, so I'm going to draw 50 degrees. So this will be our Y25. Okay. So we have to now find, okay, we do have enough space, the coordinate system for stress Y25 and the shear Y25. Okay. Right. So to find that distance, we have to more or less know. So we want to find what is our normal stress Y25. So this is equal to the P over 2A plus. Okay, so we know that this is 50 degrees, right? So the distance from here to here right is equal to our radius. We have our, yeah, is equal to R. Do we have, yeah, we do have R also. Okay, so it's equal to R cos 50, right? So I'm going to write down here R cos 50. Okay, and we also know our radius, right? So radius, so note r radius is also equal to p over 2a, right? So this is also equal to our radius, yes. So this expression come out to be p over 2a plus by p over 2a cos 50, right? So from here, we know that we can take things out. So this is p over 2a, right? 1 plus by cos 50. Okay, so that's how we get the normal stress relief. Then I'm just going to write in a small box over here, right? Because I want to use the same figure. Next, we want to find what is our shear. Okay, so we want to find the height. We want to know this distance from here to here. Sorry. We want to know this distance from here to here. And that distance is more straightforward, is r sine 50. Right. So in terms of shear, y25 is equal to r sine 50, and is also equal to p over 2a sine 50. Okay, right. So we have two equations. Okay, so we have two equations. Let me copy. So we have two equations. Now we can solve the equation. So the equations that we have, right, are stress y is equal to p over 2a, right? 1 plus by cos 50. Right. So we want to find p. Okay, so p is equal to stress y 25 multiplied by 2a divided by p 1 plus cos 50. Okay. Sorry. So we know that the stress y 25 has to be equal to the normal stress allowable, and the normal stress allowable is what was it, 800 times 10 to the power 3, and then the area is equal to 0.05 multiplied by 0.08. Okay, so 0.05 or 0.05 multiplied by 0.08 is equal to 4 times 10 to the power minus 3 meters squared. Okay, so this is in Newton, right? So P is equal to 800 times 10 to the power 3, right? Divided by 2, 4 times 10 to the power minus 3, 1 plus by cos 50. So the load due to the normal stress, so 1 plus by cos 50 times by 800 power 3 divided by 2 divided by 4 power minus 3 is equal to 164. Yeah, hold on. I got 1. Did I use the right number? Hold on. did I put the function correctly?